Okay. Um, CA08 veins to Ames. When it comes to veins, most veins are, I think, relatively straightforward in that, like Bane or Lick or Con or Gall, they kind of do one thing, and that thing is sort of conceptually it's just this straightforward thing. The big veins, Ames and Clay in particular, have a lot more going on. And so we're going to delve into Ames, which, gosh, the Ames file is, yeah, about 5,500 lines. So, this is a substantial amount of text in here. A large part of that is because there's so many corner cases when it comes to networking, and the ability to, you have to queue things up, and you have to wait and make sure that the other person got your message. And if they didn't get your message or their message crashed, you have to figure out why, you have to figure out how to handle it. And there are a lot of pieces in Ames that are just dealing with that kind of error handling. The other thing that's very odd about Ames as a vein, which we'll see about halfway through when we get to actually looking at the Ames.Hoon code, is that it has a lot of state transition handlers that are in there for legacy reasons. Because, if you change the state of the vein, you actually have to have some way of telling the network how to update itself. And as it turns out, this is also rather a complicated process, because you have to have multiple paths for things to get up to the present and everything. Anyway, we'll glance at that when we get to it later on. In some ways, it's one of the reasons that Ames is a rather bloated file, but it's not actually even a conceptually interesting part of Ames. So, in short, Urbit knows about three kinds of networking: Ames, FinA, and HTTP, which is Air Iris stuff that we'll talk about next week. The network protocol in each case has a very specific definition for the way that packets and communications work. Ames, FinA, actually, I'm not sure if FinA uses UDP, but it almost definitely does, because everything else in Urbit, like Ames, uses UDP. And then HTTP is over TCP/IP, HTTP, regular sorts of internet traffic appearance, but oftentimes your host OS is handling those communications. You don't need to worry about them as much, other than you're getting the HTTP message. Anyway, so Ames is designed for ship-to-ship communication, and it's kind of the most complicated and interesting piece of Urbit networking that there is. FinA, that we'll talk about at the end, this is the remote scribe protocol, and it's essentially a dispatcher for efficient data requests, and relies on the runtime to basically make that work in a scalable and relatively fast way. So in this lesson, we're going to focus on Ames first, and then at the end, we'll take a look at remote scribe, because that's in more flux. And ultimately, the goal is to unify FinA back into Ames the way that Ford was unified into Clay. So again, Ames, mechanically very complex. Conceptually, there's a lot of edge cases, like I said, you can think of about handling messages and so forth. But at the highest level, it's sort of conceptually elegant. It's just saying network between two ships. And this means you have to track peer state, you have to track particular what we'll call message flows, but these are message channels. But then you get farther down and you have to track individual packets and message fragments and reconstruct them, and you have to track network weather. You have to track the fact that things on different flows may occur out of order, and get into all of this. And you need to do that as gracefully as possible. So we'll start off with the network protocol Ames itself, which is, Ames is the encrypted peer-to-peer network that runs as an overlay over the UDP protocol. So we'll take a brief look at UDP later on. UDP, like TCP/IP, is a packet protocol that describes how to communicate between ships, and has some interesting properties, but it's just kind of a simple 1980s protocol. It's pretty robust. It's built for systems that are lossy. Ames does not maintain separate addressing and identity layers the way that IP addresses and domain name resolution takes place on the main internet. So an Ames address is the identity, was one of the things we like about it. We can even set aside that there's phonemic PATPs and everything. It's just, you have a number, and that number is bound to a public key so anyone can communicate with you in an encrypted fashion. That's all that's going on there. From the kernel's perspective, what Ames is trying to do is it's trying to make it possible to extend the semantics of moves across more than one instance of Arvo. Everything that Ames is doing is basically making it possible for us to establish moves across ships. So local veins that need to communicate to each other, like Gaul, will pass a plea request to Ames, and then Ames will send that message to the peer Ames over the wire, and then that peer Ames will dispatch the message to the destination vein, which is frequently Gaul. Like we're doing a lot of user space things. The advantage of using Ames is that it wraps all of these, it wraps all of the peer negotiation and message delivery details so that the calling veins do not even need to be aware of these features, right? Like if I'm in Gaul and I want to send a move to another ship, I can just do that. Ames takes care of all that for me. So to that end, Ames is going to make a few low-level guarantees that are going to translate into higher-level characteristics. So I guess I'll write it this way. How would I want to? So messages within a flow are processed in order. So like I said, a flow is a channel. It's basically I've opened up from one peer to another a set of communications. Flows are actually more complicated than that. You may have multiple flows between peers and so forth. But essentially, you're thinking of a flow as a channel, and you can process everything in order within that flow, even if packets arrive out of order, right? Like if message fragments arrive out of order, messages are numbered within that flow, and so they will still resolve in order. However, go ahead. Was that a question? Oh, that was just unmuted. Okay. If you have two different flows traveling, then you don't know that things are going to take place in the same order, because network traffic can get in the way of that. You also know that messages are delivered once to whatever the destination is, whatever the destination vein is. We know both ships are transactional, so this means that once we have received an acknowledgement that the message has been delivered, then we can clear it from our cache buffer. We can forget about the details. I mean, it gets written in our event log, but we don't have to keep it in active state, ready to pass it forward. So it's a nice guarantee from the networking perspective. We've talked with Arvo a lot about ducts, and that ducts give us this way of thinking about passing causal information forward and backward, and dealing with having able to have ordered sequences of events that travel things forward and backwards. Networking is in some ways like a duct. It does require us to keep track of the forward and reverse causal history. We need to know where things are going. We need to know where acknowledgements or crashes, negative acknowledgements, are going to return. But we do have two different kinds of data transmissions. And so if you go back to the white paper, this is something that the white paper makes a big deal out of when it's thinking about how to organize what's going on with Ames. A lot of the technical details of Ames have been refined since the white paper. The white paper is what, 2016, I believe. So there's a lot of technical details, like the size of packets or the way they're transmitted, that may not necessarily be the same. But the high level discussion of like what Ames is doing is still pretty good. Anyway, so it makes a lot of difference between commands, which are transported over a bus, and packets, which are transported over a network. And so a command is, if you receive a command more than once, then you need to execute that thing twice, right? Like every time you receive a command, you need to execute that command. And so this is more like what's happening within Arvo on a ship. When you enqueue moves to process into events, you're enqueuing commands and you want things to process more than once. Packets on a network are a little different because you don't know, for instance, if a packet is going to be received on the other end. You may, on a timer, transmit a packet more than once before you receive an acknowledgement that the first time you transmitted the packet was received, right? So, you've got, let's say you've got a 5-minute timer at 5:00, at 4:59, the other ship issues an acknowledgement that it received your packet, but you don't know that. So at 5:01, you send a second packet. You actually want the remote ship, in that case, to drop the packet when it's received, right? You don't want to process that twice. And so this will be reflected in the way that Ames is going to organize, numerically message flows and everything. That we'll see this reflected as we start to look at the architecture of what's going on. Ames also has to be able to send packets of, let's see, I read somewhere that exactly once delivery will be relaxed will no longer be a guarantee. Is this true? That's a good TED question, and I wish you weren't off this week, because that's Ames is actually one that he would have I think a lot to say about, as opposed to something like Bain or Dill. So in a sense, you don't care about exactly once delivery. You care about at least once delivery, right? Like if someone gets the packet more than once, they can decide what to do with it, right? They can drop it. They can, like learning, the way the white paper puts it is learning a fact twice is the same as learning it once. And so there's probably some ways that you could make the network traffic more numerically efficient by relaxing that guarantee. So like basically your life cycle, we'll come back to packets in a minute, but let me look at, let's look at like what the life cycle is right now for ACKs and NACKs. So if I have here, this is an acknowledgement. So your basic life cycle is going to look like, sorry, I'm trying to find a specific line in my notes here. Because I want to make sure I say the life cycle correctly. And I think I can't see it because all this Zoom stuff that's in my way. Well, it's somewhere. Anyway, I'll find it. Your basic life cycle is you're going to send Ames. So I'm gonna call this a local and a remote peer. I could call it a peer, but like a local and a remote. So your local Ames is going to send a message as a transaction to another ship. When that is received by the other ship, and we'll look at like what transmission looks like. When that's received by the other ship, then it is processed into an event. A successful transaction just gets you an ACK. It gets you, well, okay, actually I should say a successful receipt on the remote gets you an ACK or an acknowledgement. So you get a notice back that this packet, this message was received, assembled correctly. I have everything. I don't need you to keep transmitting it on a timer. And then if that transaction completes properly, then there is no further result. I mean, it might result in like a gift or something like that, but there's no other kind of thing fundamentally that happens with it. You know, it's processed as a normal move. If that packet goes to the other side and fails to process for some reason, this results in a knack. Okay, so then the knack means something broke. It resulted in an error. And then that's going to open a new message flow. And in that message flow, there's going to be a knack explanation, what it calls a knack explanation here. So that's going to come back in a separate message flow. This is what I mean by like we might have multiple message flows back and forth between the system. So you're going to get a knack explanation back, and this is actually going to give you the tang, you know, the list tank of the error crash, the error trace, and then you're able to figure out exactly what happened in that case. Ames is going to adaptively continue to send messages on a timer until the appropriate ACKs or NACKs have been received. So Ames, until it gets an ACK or for some other reason decides to close the flow, is going to keep attempting to send the message. So, you know, if you get a breach notification, then this may change, you know, like you cancel your flows. You decide that you're not going to deal with them anymore. That's called corking. Does that answer your question about the exactly once delivery?
Yeah, I think so. Thank you.
Okay. And so, yeah, so basically ACK equals successful receipt. NACK equals unsuccessful processing. And so they mean a little bit different of a thing because of that gap there between a NACK is presumably successfully received, but then fails to process. An ACK is a successful receipt that succeeds in processing, but you don't know any more about it unless you get a response back for it. This is different. One of the things that's highlighted is that this is different than TCP. A TCP NACK means that you're missing a numbered packet. So Ames doesn't handle that the same way. If you don't get an ACK back, that's not getting an ACK. The absence of an ACK is analogous to a TCP NACK, if that makes sense. This terminology is terrible because you end up saying these things right on top of each other all the time. But basically, that's what's going on. So Ames doesn't have this because failure to get an ACK is the same thing as this missing a packet. Okay, so this is related to the exactly once delivery, but I'm guessing if you relax exactly once, I don't know the detail. That's a great Joe question. You might be able to save on some network traffic or something.
Yeah, I don't know the details. I just heard that like there was some sort of paper going around about like trying to relax this. I don't know if it's even happening, but just curious.
I don't think there's a whip yet, but I think that Logan from Zorp doesn't like it, and Philip Monk doesn't like exactly once delivery either. So there's talk, is my understanding. I'm a fan of it. I've like worked in systems where you don't have it and it sucks.
Well, what is getting rid of exactly once mean? Does it mean more than once, or does it mean that we're not dealing with missed messages and we're going back to like TCP NACks?
I don't know.
Right, like there's a big difference in those two directions.
Very much so.
So there's some interesting consequences because of this ACK-NACK system as it currently stands. Urbit, from a ship's perspective, is sort of perpetually on. Like you're actually assuming several nines of uptime for your session because you can essentially guarantee that if the ship comes up anytime, then you can get that message through. Right, like you can make that happen. one of the points, and I think this goes back to Phil's. Now I remember Phil making a related point to the exactly once. He said at one point that applications don't care about exactly once. That what applications care about is whether it gets there or whether it was. They don't care whether it gets there. What they care about is whether it was completed. Right, like whatever completion means. I think that's probably the related to the exactly once thing. Like I think what. So I don't know if that would mean that we would convert acts to successful processing instead of successful receipt. But I do kind of remember that now that comes up. I'll find that and put that in the notes.
I just hope I don't get like 2 pokes for 1 poke. You know what I mean? That's gonna be kind of tricky to handle.
I don't. Well, that goes back to the command versus packets thing, right? 2 pokes or 2 commands.
Right. Yeah, if it's just like, yeah, I don't understand the nuances. Well, I understand the commands versus packets distinction, but like for this exactly once delivery, it's like if it's exactly once for commands still, even despite these changes, then that's probably fine. But,
so from a networking perspective, what you're dealing with is the problem. If you go back to like 1999, if you bought something on the internet with your credit card and you refresh the page, you bought something twice.
right.
Like this was a problem that it actually couldn't distinguish multiple, like that was 2 commands. It didn't understand that there was one command that you were sending as 2 packets. It understood 2 commands.
Mm-hmm.
And so that is kind of that's kind of an engineering problem to decide like exactly where to resolve that ambiguity. So I guess you could say there's exactly once, but there's at least once, and there's at most once. Are kind of the two solutions to that.
I can see the at least once. How would you do like an at most once?
At most once would mean you fail to resend.
I see. So you just send it once, and you just hope it gets there.
Right, and you don't know if it's there.
It's how UDP works.
Yeah.
It is. Yeah, that is actually how UDP works.
Yeah.
Which is why we have a lot of message flow management layer in Ames on top of that. Because UDP is actually designed to be a flaky system. Because it was built in the 80s, right? It was built like you don't know if your mom's going to pick up the phone in the middle of your gaming session, right?
It's like UDP is supposed to be the unreliable one. TCP is supposed to be the reliable one, right?
Right. Let's go back to. I'm doing this out of order, which is absolutely fine. I don't care. Let's look at UDP and then let's look at Ames packets then. Okay. Because we're at UDP. All right. So UDP has the wonderful acronym for User Datagram Protocol. Imagine calling something a datagram, right? I mean, this is like a neuromancer kind of terminology here. Quote from the specification: transaction-oriented delivery and duplicate protection are not guaranteed. My theory is that this is actually why they settled on ACKs and NACKs in Ames working the way they did. Like this was just, they decided to use UDP because it's a nice, simple protocol. And then they had to build this ACK-NACK system on top of it just directly to deal with that. So a UDP packet has a header that's your destination, your source, length, checksum, and payload. Like that's it, right? Like it actually has like five data inside of it. It's like your minimum viable packet protocol. Nothing else is going on. There's no handshakes, there's no anything. It's just there's a header that's like, I think it was 4 16-bit fields was the header. Like that's the guaranteed size, and then the packet size. So it's also faster than TCP. Another funny thing about UDP is it gets treated differently on networks. So I don't know if you've experimented with this, but I've noticed that when I'm able to connect to a wireless network, but I'm not able to authenticate, I can still use my Urbit stuff because it's communicating over UDP instead of TCP. So if I'm in some place where I can connect to Wi-Fi,
Wait, really?
yes, I've done this several times.
Oh, this is interesting.
So what I can do is I can tail scale in,
Yes.
and then I can use Urbit.
Okay.
There might be some
Interesting.
interesting consequences of this, but I have done this multiple times.
I like this idea.
But wait, isn't like you mean you can use landscape?
Yes.
I thought isn't that TCP?
Well, all the Urbit stuff's on the back end, and if I already have landscape on my front end, like
Okay. Yeah, if
right?
you already have the
right, like it
if the
wouldn't
tab is
load,
just gone, is doesn't need a hard refresh.
right. Like my session,
You just
my
restore the
client
session.
session, right? So if I'm using like the Tlon app, which already
Yeah.
has all that built in,
Yeah.
then I'm just
Eh.
doing UDP and everything, and it seems to work
That's
okay.
the closest we'll get to freaking.
I mean, that actually, you're right. It is kind of like that. Someone should write a paper on the red box. Just push everything through UDP. There's probably some really interesting stuff you could do if you wanted to take advantage of that. Yeah, so UDP is actually used in like VoIP and other contexts like streaming, where dropping packets is better than fidelity. So it's where you're tolerant of loss. And so that's why Ames does what it does here. I mean, so it would be interesting too to think about like what would a variant of Ames that was TCP compliant look like. It might even be worth the experiment at some point just to build one and see what it does. It's probably a bit much for a homework, but
It'd be a big homework. Don't make us do that.
And it turns out that you actually don't need to know almost anything about UDP to make this work, because all the UDP stuff is handled in the runtime, and most of it's handled in libuv, the queuing of everything. So you're getting packets, the runtime is unwrapping them for you, and then when Ames is doing all its assembly and everything, you already have it as like the Urbit payload pulled out of those UDP packets. So you don't really need to mess with UDP. You just need to know like it is what's being used, and it has these characteristics, and that's why it gives rise to the way that Ames is. There's a lot you can do with a stateful UDP server, especially one whose semantics are reasonably formal. CGY. Is that what is that quote from? Is that from the white paper or? Just ambient. I think I found it on some university related forum from like 2012. That's I mean, it's true. I'm gonna pull that. I'm gonna stick that in the notes.
There's a whole section on exactly once delivery in the white paper.
Yeah. I mean, I read the white paper to do this, so I know some of that stuff's in there. Okay. Interesting. All right, so now let's look at Ames packets, right? So the receipt of an Ames packet is an Arvo event, and the emission of a packet as a response is an Arvo effect. The runtime is responsible for all how do you actually get the bytes? Like you've constructed the packet, how do you get the bytes in the packet across the physical network to another ship? That's runtime level stuff. We'll look at it a little bit, but that's a pretty mature part of the system, unless you did want to rip out UDP and do something else. So an Ames packet is going to have a 32-bit header and then a variable length body. There's let's see if this table, that's the wrong. See if I can copy it. Okay, close enough here. All right, so there's your high bits are reserved. It's never made clear what they're reserved for, but it might have something to do with the fact that the 28th bit is Ames or FinA, so maybe this is a hedge against future possible protocols, but we leave them as zeros for now. There's an Ames protocol version. Right now, the Ames protocol is 0. If it's still 0, it's possible that it might be 0 for a long time yet. The sender and receiver address size is kind of interesting. This is basically if we go to, I think this is in LOL. Yeah, ship meta produces that 2-bit piece. So basically, if it's zeros, then you're a galaxy or a star. If it's 1, you're a planet. If it's 1, 0, you're a moon. And if it's 1, 1, you're a comet. This is going to be used in the payload because part of the payload like has an internal header. There's like a secondary header that has the addresses and if this is a relayed value and etc. So in the main header, you're just getting how big is the address that I need to pull. And then in the secondary header inside the body, you'll be able to get the other information. There's a checksum, and then there's a bit that gets set whether or not this is a relayed value. So of course, if you are a galaxy that receives a packet on behalf of someone else, then you actually need to open it up and relay it to the ship in which it matters. If you relay, there's going to be a value inside that has your last known IP address of the host. So you're attempting to make it resilient against IP address persistency versus change and everything. All right, in the body, all right, so that's header. And then the body, like I say, is going to have a secondary header, which is this first part here. So your sender life and your receiver life. Mod 16, which has the interesting characteristic that you might be able to actually overflow and reset yourself back to 0, old school video game style. I'm not sure if anyone has ever actually experimented with this. It's kind of a Y2K problem kind of situation. Like, how do you actually get to a big enough value? But these are bits, not bytes. So what is RAPSEF? Was it like 25 breaches or something? So maybe someone will get there. I mean, I guess if he's at 25, he got there, and it didn't make any difference. I mean, I guess the main thing that you want to be robust against is that you aren't accidentally sending, that you know that you're on the current life, and you're not one off either way. All right, then the address sizes for the sender and receiver are determined by the receiver sizes up here. And that's why you have those. And so even for a galaxy, it will still be as wide as it would be for a star in those cases. Then there's the origin information. This is it's the address in the port. There's like a standard fixed size. It's like 32 for the address and 16 for the, I guess it'd be 32 if it's IPv4. So it's 32 for the IPv4 address and then 16 for the port. And those are fixed. There's the cryptographic AES-256 vector stuff. Matt, this is where a lot of that crypto that we were looking at, the SIB stuff, is actually turning up, is in this Ames encryption here because of that. And then your actual, like, what is your encrypted ciphertext? What are you actually sending? The ciphertext is formed by jamming a packet and then encrypting using the AES stuff. So pretty straightforward. Once it has been jammed, then it's going to break the result into 1 kilobyte or smaller payloads. So the maximum size payload you should get is 1 kilobyte out of this. The packets are numbered. I'm not actually sure where the number goes here. It must be unencrypted, and then I guess you unencrypt the packet, and then it must have the number inside of that there. It's you queue it back into a shut packet. So I guess let's take a look at shut packet, which might be in lol, and then we'll see where that number is. So shut packet. Okay, so a shut packet is a bone, a message number, and then the meat. A bone is a message flow numeric identifier. So it's a message flow identifier. It's a number within that flow, and then it's information about the fragments. Okay, so when you get the packet, when you get the ciphertext, you get your fragments, you assemble them back into a large atom, then you queue it into a shut packet and use it that way. Okay, that's what's going on with those. All right, a little bit complicated with that. Anyway, essentially that's what's going on. Yep.
Quick question here, Neil.
Yep.
How is the channel number negotiated between the ships? Do they all just like assign their own? Like, because it looks like it's embedded somewhere in the packet with the bone. Is that right?
Yeah. The bone is the identifier on. They should not have the same bone, I think. Well, bone is per peer. Bone is per peer. So actually, I think you should. Because your message flow is per peer. And so the bone that you're on per peer should agree on both sides of that in that sense.
Mm-hmm. And do we just like increment while there's still active packets? I'm like trying to figure out like how do we know like what number to choose, right? Communicating between us two ships.
Okay, let me jump to message flow stuff in a second then.
Okay, yeah.
Let me finish packet stuff here, and then we'll go to message flow, which is fine. That's a good logical next one. Okay, so what you're going to do is you're going to get back out a raw noun. So you're going to queue the reassembled message fragments back into a noun. It's a raw noun, and then you're going to treat it as a cask, which is a pair of mark and noun. It's like a cage. A cage is a pair of mark and vase. A cask is a pair of mark and noun. So now you're going to use your mark to rebuild this noun. So this is us requiring the recipient to build the code locally. We don't, in a sense, I mean, it's homoiconic, so this is almost a distinction without a difference, but we don't transmit code over the network, or put another way, we don't transmit vases over the network. And I think there are reasons of upgrade for not doing that too. It's not just security, but you're expected to build the code locally rather than sort of like accepting hot code over the network. So Ames messages are typed, but the type is not sent. It's more like a MIME type, where it's a label that the recipient has to map to their own local source path. So the main problem with that is that you may not have received a protocol update, right? So you may have different versions of a mark. And so you're going to drop packets in that case and just have to figure out how to renegotiate that after the upgrade, after you're both on the same protocol. Communicating across protocol upgrades is like actually a hard problem, as Phil has talked about in the design of groups. And with groups publishing, you simply don't publish across version upgrades. Like that's their solution right now. Is rather than trying to support multiple versions of the protocol, you just simply can't publish across versions. All right, let's go to message flows. The funny thing is we have not even looked at a lot of code yet. There's a lot of code to look at with this too. Hi, Puppy. What do you want? I think you want to go outside, but I do not have the bandwidth to let you outside right now. Sorry. Why don't you sit? Sit. There you go. All right. All right, message flows. Let's go to message flows. So let's go to, gosh, you are going to be a pill right now, aren't you? All right, so here's your basic pieces of message flow. So you have a bone, you have fragments, and you have message blobs and message nums. All right. One of the interesting things here is like, look what's going on with these atom auras. Right? Like we're actually using auras in a really interesting way to just like uniquely, like you cannot confuse these values with each other because they all have an aura on them. We don't see this done in a lot of places in the kernel, but Ames does it a few times. I think jail does it once too, but I think other than that, this is not really a common pattern. Probably makes sense because otherwise these are all just raw integers, and it would be really easy to confuse them if you weren't being careful about the type. Okay, so a message, let's look at the message management. Then we're going to go back. Don't let me forget to go back and talk about routing too. We want to talk about routing. So messages are broken into fragments, and then they are sent to a lane. Okay, and a lane is each of a PAT PC and an address. Okay, so it's a PAT PC or it's an address here. A PAT PC, what is the PAT P capital C doing for us there?
Address width?
What's that?
Or no? Is that the bit width of that value?
Yeah.
The capital C?
So it's a galaxy, so that's our 2 to the 3rd. So that's a 2 to the, or 256 width there. And, or an address, which is the IPv4 address. Addresses are, yeah, it's a PAT UX address. I don't know why they don't use the PAT IP ARA, which we have as well, but anyway, there it is. So we have a lane, we have routing. We're not going to deal with routing yet. We'll deal with routing in a minute. But when you have a message flow, so you're opening a flow between peers. You may have multiple flows between peers. Ames is going to have a bunch of lanes, and every lane is going to have a number of bones, and a bone refers to which flow you're dealing with. And Ames is going to queue messages into a message flow by bone. And then it's going to transmit the fragments that it needs to on timers or by whatever's next or in response. Like it's going to set those up and it's going to be sending those out. Probably a good one to look at in Ames would be split message. That would give you an idea of how this is set up. All right. So split message into kilobyte size fragments. All right. So that's what this is going to do is you're going to get a message number and the blob. So this is the nth message in this flow, right? We don't need to know the bone because this is just, I need to put my message number in my atom, but I don't need to do anything else. So I have my atom data, my jammed atom data, and my message number. And I'm going to break those into pieces and send them back out. Now, what's neat about this is it makes a point here. We don't literally split it here, since that would allocate many large atoms with no structural sharing. Instead, each static fragment has the entire message and a counter. And then we offset and encrypt to get the actual fragment, which is kind of a neat optimization, right? So you actually just, you don't want to allocate a bunch of unique atoms. So you allocate one large atom and then you take your offset inside of it in 1 kilobyte fragments based on the counter. The assembly on the other end takes place, I guess let's go to here first. Here's where a fragment comes in, okay? So along a lane from a source, you're going to get a packet. You know it's a fragment, okay? Now what you're going to do is you're going to add up the number of fragments that you have and see if you've actually gotten all of your fragments. If you have gotten all of your fragments, then you're going to send an ACK, and you're going to end up passing this through. Send the shut packet is send an ACK, and then you're going to send this to. I'm looking for the call to assemble. This is all dealing with, we have partial messages here. And it's going to end up making a call to, see, this is what I mean by like, there's a lot of complexity in Ames where like here, you have 20 fragments in this message that you're going to have to put together. So there's a lot of checking, is it in my map? Am I putting it in my map? Is it my map complete, et cetera? It's doing all of this management here for you. But where it's going to end up is assemble fragments. So assemble fragments is what is actually going to put the fragments back together. And so this is going to just manually sort and build the values together. And then it's going to sort them out. Might actually be interesting to see if you could do this more efficiently with a mop instead of a map, now that we have a mop. I'm assuming, the last time Ames was rewritten was Aleph in late 2019. And then Ames is currently being rewritten with the namespace directed networking that Joe talked about at reassembly. That I don't know when that's going to go live, but I think maybe by the end of the year is what they're targeting for that. And so it'll change aspects of this and add some sophistication to it. But anyway, then you're going to rep your system and queue it, and now you have a value, right? And you're passing this back out as your raw noun. So literally your assembly is resulting in a raw noun. You've heard all the fragments, you dump all the fragments in here, you get your raw noun back out. And then you have to, wherever assemble fragments was called, you have to decide what to do with it. So that then results in your message, and then you have to figure out where do you enqueue the message and everything. So, I think that's there's some neat optimizations in both of those, in the way that those are put together. Those are kind of more elegant pieces of the system. Now, okay, we talked about nested cores with Bane. All right, and so Bane had this abet pattern that was, I think, reasonably flat. It had an abet. I don't even remember if it had an abed. It had an emit. It didn't do a lot, but it built a list of cards, and then it returned out an object with state changes made. Ames has a much more sophisticated engine pattern, a bet engine pattern in it. And if we count up the number of abets in here, there should be 5. And so there's 5 cores that are going to handle things for us. So there's an event handling core, there's a message receiver core, there's a message sender core, there's a per peer processing core, and then there's what's called the packet pump. And the message sender is the message pump, and then it's going to build out messages into packets, and then it's going to send all the packets to the packet pump, and the packet pump's what's going to make the decision about, when do I decide to send these on the network and queue them along different message flows. and everything. So we're gonna run into those. What is still missing in here, and I think clay goes to the next level of sophistication. So basically you can have like the simple nested core pattern where you used to have a bet, emit, whatever. You can go to the level where you have multiple abet cores, and then you can go to the next level, which is where all of these are prefixed with names like these. And these make it far easier to keep track of what's going on at that point. Because, presumably you have a number of these that you're interacting with at different times. And so by the time you get to clay and clay's level of sophistication, that's what you have to deal with is label, internal labels for the abets and emits and everything inside of this. So Ames is kind of in the middle of that degree of complexity. The other thing I need to look at is, let's look at the message pump state. I think that's in LOL. Yeah, so it's one of the nice things is Ames is actually pretty literate. Like it's actually commented fairly well to explain like what the intent is for different things. But the basic idea of the message pump engine is it's going to manage unsent messages. And then when you get to the queue, then you're going to be able to send them to the next, to the packet pump and get them sent. And then you have an unsent fragments queue as well for things that the packet pump can't send for some reason. And then it deals with where do I have ACKs and everything. So this is basically just your Arvo specific message dispatcher, and then there's an Arvo specific packet dispatcher that sits next to it that handles just like what am I actually sending at any given time. Like I say, there's a lot of edge cases. There's a lot of consistency and sanity checks on messaging. Once you've gotten to the end of a task, it's going to send a halt task to packet pump. And then packet pump will have timers based on congestion control algorithms and everything, and deals with everything. Yeah, oh, here's an interesting one. Okay. Why do my messages start with the default value of 1? You think about this from a message sequence standpoint. All right, you never want two messages to have the same number, which means you don't want to start counting from 0 with your message system. And so there's a few places where it's going to explicitly call in 1 because you want your next message to be sequentially greater by at least 1 than the last acknowledged message from the receiver. There's a lot of interesting things like, yeah, so there's a static fragment which keeps track of, how many fragments do I have? What fragment am I on right now? What's the content of that fragment? There's a partially received message that's interesting. Yeah, here. So, this is tracking. I've started to get some fragments. This is the kind of thing that we were glossing over in here a moment ago, right? That I have a number of fragments, I have a number of received fragments, and then I have a map of these things. This is how I'm queuing them up so that I can pass them forward there. All right. And then I also want to talk about bones and corking. Actually, also while I'm at it, QoS. QoS is your quality of service. This is keeping track of how my connectivity to a peer is. Right? So if a peer is unborn, then they haven't spawned on Azimuth yet, and there's nothing I can do about them. if they're live, then I have a last contact. Anyway, so this is all things that we're tracking. Let's see, Matt asks, how much of Ames Hoon is actually implementation specific? Ames.hoon is, I think, essentially agnostic to the packet protocol that's underlying it, the transmission protocol. I don't think there's anything in Ames that is really UDP specific. Yeah, see, one runtime implementation sends UDP packets. Yeah, the runtime side is enormously UDP reliant. Ames.c relies very heavily on UDP, and that's what you would have to rewrite if you wanted to do this.
Yeah, nothing in Urbit knows what UDP is. Like, there's no concept of an IP for UDP to even work.
Yeah, maybe Joe will make the runtime side protocol agnostic too. Yeah, so maybe. I mean, you have to have a handler, right? So you might say, well, we're going to make Ames.c talk to an API that negotiates between things. But that API is going to have to know about UDP or whatever, right? Like it's going to have to know about some protocol to communicate. So it's just a question of like, how much do you want to abstract that out of what Ames sees? Like Ames.hoon doesn't care. Ames.c does care. Ames.c could not care, but something in the runtime would have to care. Ultimately.
Yeah, so I think by protocol agnostic, it means you can plug in any protocol you want, and we may just go ahead and, plug in UDP for now and there, but it could also have others plugged in too.
Urbit over Gopher.
Yeah,
Um,
etc.
Urbit over USB sticks.
Urbit over
Pass
butterfly
USB sticks
wing
around.
do it in a UART.
Yes, exactly. Yes to all of the
Urbit
above.
Urbit on Bluetooth.
Yes, to all of the above.
I mean,
Yep.
I guess the question is sort of like, what do you gain? Yeah, steady hand and a magnetic needle. You have to interpret the perturbations in the Earth's magnetic field as zeros and ones. Like, what do you gain by switching to other protocols? I guess is the question.
Other devices can talk to you. I can respond to an embedded chip that only speaks Bluetooth.
Is there an embedded chip that only speaks Bluetooth?
I can write one. I can make one.
I mean, you
Bluetooth and
could,
Wi-Fi, yeah.
yes.
But I mean, I can speak to a chip that only speaks UART.
But it's sort of contrived, right?
Very much so.
I mean, it's like, is UDP? I mean, UDP is simpler than UART.
No, it's not.
Is it not?
No, not at all. Not in the slightest.
I mean, I
UART
guess I don't know
literally-
what the transport layer, but like the UDP definition is quite simple.
Yeah, UART definition is even simpler.
I mean, UDP is like sender receiver message length. I mean, it's like,
Yeah, the other one is start bit and then your bit. But
but
again,
you still have to know addressability and stuff. You have to get that out of
No, you
something.
not. I mean, again, we're comparing transport layer versus a higher layer.
Yeah.
Yeah. So
But anyway, this is what you'd have to mess with if you wanted to implement Ames over something else. Ultimately, that's the short answer. So right now, you can talk to something with IPC, for instance, but you're not talking Ames to it. You can talk nouns to it, but you're not talking Ames to it. Okay, QoS matters. Let's go back to QoS. Maybe that's in law. Okay, the QoS. QoS matters because if you have a bad flow for some reason, then you're going to cork the flow. And so this will turn up a lot in discussions of networking efficiency and, you know, under what circumstances do we cork a flow, or we cork the flow on one side but not on the other. You know, like sometimes when a Kelvin decrement breaks something, this is the sort of thing that goes wrong, is like corked flows get inconsistent with each other. The bone is your identifier, and so there's this wonderful data structure called an ossuary that is keeping track of basically how do you map bones to ducts on your system. So you have a message flow. Given the bone of the message flow, how does that map to a duct on your system, and how do you pass these things around? And what's the next bone, right? Like what's the next sequential bone that you're going to refer to? Yeah, so we actually, Kirsten and I on Thursday last week went to Evora and saw the bone chapel. We saw the ossuary there, and you go in and it's just this big room, and the pillars and the walls are completely made out of human bones, which was like actually quite disturbing. Like I think it might be the creepiest thing I've ever done. I mean, it's a memento mori, of course. The inscription on the outside was no sosos aquí esperamos. No sosos aquí estamos, pelos vosos esperamos. We bones are here, we await yours. That was in Evora. So Evora is the city that Magnus was pushing as the Urbit colony back at Volcano like 6 months ago.
Wow.
Anyway, so I was like, oh, I'm gonna go take a picture of the ossuary. So I have this cool picture for my my talk here. And then I got there and I was like, I think that actually taking a picture of this would be like not appropriate. Like, you know, like it just like felt like this. And then like, you know, like and then like the Chinese tourist walks in and he's like videotaping the whole thing. Like he's experiencing the whole thing through the camcorder, through the phone.
Well, like churches are terrible places. You know, that's a common adjective you
Right,
find
right.
in the liturgy.
Yeah.
Yeah.
So anyway,
I imagine extremely terrible when it's walls of bones.
Yeah, I mean,
But
like
you also
was
missed the opportunity to
awful.
send Jose a picture and say, hey, get your bones, like, you know, straighten out the bones here.
I mean, there are bones on. I mean, there are pictures of this online. I don't have any qualms about those. I just didn't feel like at the time.
Yeah,
like,
no, I see 'em.
I wanted to take a picture of this thing. Anyway, so long story short, here's an ossuary in Ames. So it's keeping track of the ducts and the bones. Okay, interesting thing about bones is bones increment by 4. And this gives you 2 bits in between that you can use to pack information about whether you're going forward or backward, and whether this is a normal or an explanation error trace flow. So you can divide with remainder and use the remainder to encode additional information about what kind of message flow you have, which is another neat trick, bit packing trick. Okay, so we talked about corked, we've talked about ossuaries, we talked about bones. So, you know, if you go look around at like the kinds of problems people have, people talk about things like dangling bones. So that would refer to an incorrect bone, like a message flow is closed on one side, but not on the other, or closed before all message fragments were received. So things like flows are supposed to remain not synchronous, but synchronized across both ends. Like if it's open on one end, it should be open on both ends. And there's a lot of plumbing in Ames to make sure that that remains the case, that you don't end up in inconsistent states there. And so then there's like some congestion control stuff. I think pump metrics. Yeah, pump metrics are your congestion controls. So this is dealing with what's your timer, yeah, your transmission timeout, your weight, your congestion window, all of that kind of information is kept there. And then the packet pump uses that to decide whether or not it needs to send things forward there. And, it points out this is a variation of TCP's new Reno algorithm, but there's been a lot of work done on how do you efficiently send and resend messages ever since Claude Shannon and Bell Labs. So did you miss a joke? Which joke were you looking for? Reno? What was the joke?
I forgot what I lolled at.
Um,
Oh, the Chinese.
oh,
The
the
Chinese
guy,
tourists.
the guy taking the
Yeah. Yes.
I mean,
Yes.
there were lots of tourists doing that. I was just there at the same time as like a Chinese tour bus had come through. So
Oh,
that's what
that is classic.
that's what I really noticed.
Yeah,
Anyway.
they're good at tourism.
All right, let's see. We need to talk about routing, and then we can actually talk about Ames. Like, how do you interact with Ames? All right, where are my notes on routing? Okay. All right, so you have an address. There's two kinds of addresses here. One of these is inside of, I think this is the one that's inside of Ames. No, this is the one that's inside of Air. So the Air address is not the one we want. We want the Ames address. So we want, this is our Ames address. It's opaque in the sense that it is an IPv4 address for the runtime to use, but it's opaque in the sense that Ames doesn't know or care about what this is. It just has to be consistent with it. Anyway, so routing is going to be determined by, you're going to have a lane, and the lane is either a hard-coded Galaxy address or this IPv4 address, which is your last known address for that value. Galaxy addresses are provided to the runtime on boot. There's an RPC call that is made to a roller or to an Ethereum node. We can look at that in dawn.c. Do I have dawn.c open? As a matter of fact, I think I might not have. Let me pull this up. I don't have the. I want to add folder to workspace, and I want to add var.
So does that mean that these Galaxy IP values are encoded on chain?
Yes.
Interesting.
Because basically you have a bootstrap problem, right? Like, how do you actually know?
Wait, Galaxy IPs are not on chain.
Galaxy addresses are provided by a roller.
No.
Yes, I asked Joe about this.
I thought Galaxy addresses were assumed to be galaxy.urbit.org.
Well, it doesn't look them up that way. It looks them up from Azimuth.
Really?
Yeah, I asked Joe about this.
Then why do we have a whole? Then why? I'm so confused. Okay.
I mean, maybe that's reflected in the same thing. Let's look at Dawn ETH RPC, because this is where the actual call happens here. Ethereum JSON RPC with request response as aux. So basically you're going to make a call out, and you're going to get the buffer back, and then this buffer just gets read pretty much straight into the Yeah, there's a galaxy table right there. So
Oh.
we call the RPC and then we do a need unit to get the value out. And assuming we succeed, then we can unpack that into the galaxy table.
Were you thinking galaxies were expected to have some sort of like protection against IP?
No, I was just always under the assumption that it was. I mean, I didn't realize it went through Ethereum, but I know that there's that galaxies are assumed to be like it's an axiom that they're at galaxy.urbit.org.
Yeah, that's right. Why
I
is
didn't
that? I
realize
wonder?
that the
This might be
runtime.
retrieving. I mean, I guess we'd actually have to like go hit this URL and
I wonder why that is.
Yeah.
where's URLC URLC defined?
It's still that way? Maybe it just used to be that way. Yeah, like why is that set up like that?
Set opt. Well, that's with an option.
Huh. I mean, today I learned.
Okay, I actually don't know where the
Yeah,
curl opt is coming from.
I thought that's what the czar was doing, was just getting that table.
This must be pulled in from a library. Well, this is a generic. Let's look up URLC. Anyway, let's see if we can. It'd actually be cool if we could find the actual place where this is set.
And that looks like that's where it was.
Where in
Yeah, main.c.
well, this
Up
is
one.
pulling it
Up one
from
more.
no, this is pulling it from your args. This is when you're doing an override.
Gotcha. Okay.
Like, it's not actually clear to me where you're setting
Yeah.
the original value. I guess it's this. It's
Yeah.
okay, so this is your actual roller. Okay, let's curl this. Let's see what we get. I guess I don't care where I'm working. Well, that was uneventful.
I have to do.
Do I need to do something special to get it as a JSON?
FX something happen? No, let's see. We know that's post. We don't want to post to it.
We don't want
just
to
wanna
post. Yeah.
Get, I'm
gonna do this in a browser real quick.
oh, hep, capital Hep, capital H. Here, I paste it.
Oh, okay.
Maybe.
Maybe.
Oh no.
I don't know. Okay.
No.
Well, it also might be a pending. There might be somewhere else that it's appending something to this URL.
Yeah.
Anyway, it would actually be interesting to know more about that. But I mean, like when we get to jail, we're going to run into this too with Azimuth, which is that jail actually sort of doesn't know about Azimuth. Okay, so if I go to roller.urbit.org, it's actually a login page for Diltex Famtiz. So this is just a planet that's exposing the internal roller.
Yes. That I knew because it went down recently.
I remember that, yeah. Okay. So this is just exposing. So it is getting it from Azimuth ultimately, just through the ETH roller stuff. But de facto, what it's doing is it's hitting a URL to get that info, and then just getting it over HTTP. Anyway, so what I was going to say is with routing, then your Galaxy addresses are provided to your runtime on boot. So this means you always have a findable route to points that have active sponsors. The Galaxy ports are hard coded to be at it's like LEET plus the Galaxy numeric offset. So you should also be able to find your Galaxy by port. Like it's like yeah, so like Ames hard codes that here. So it's like one or the other, you know, it tries both.
No, it doesn't try both.
No, I don't know what net is.
It's if it's
Oh,
a fake
local.
ship or not.
Oh,
Yeah.
okay. This is local or not. Okay,
Yeah.
okay. Well, no, the local's not a fake ship.
It's
Right,
also, I mean, it's also for fake ships.
Yes.
Yeah, sorry.
Yeah.
Yeah.
I guess that planet must be on L1. It seems like there's something of a cold start problem with hosting the roller on a planet. Yeah, maybe. I don't know. I don't know enough about the roller stuff. We'll get into the very last lesson has jail and azimuth in it, so we'll get deep in the weeds on that at that point. Mostly azimuth actually doesn't care about Ethereum. It just cares that it gets a source of truth. And it chose Vitalik for its source of truth. All right, let's see. Let's go back to LOL and actually look at, okay, now we can look at Ames. All right. The definition of Ames in LOL. Do you remember we did like Bane and it was like, you know, like 30 lines. The definition for Ames, the Ames interface in LOL is like 500 lines. It's huge. And partly it's because it's actually documented, but partly it's just like there's an awful lot of data structures that it wants to have in the header so everything can see them. Now, here what that means is we're up front, we care about the tasks and the notes. And we're going to ignore the remote scry tasks for now. So we can do a lot of these things. We actually unless you're actually working on Ames, you're not going to use most of these. Like Cork is used internal to Ames. From outside of Ames, you're going to care about here. Maybe heat and jilt if you're doing tuning stuff. So here is your main, like I've gotten a packet from Unix. Like a packet from Unix has been injected into Arvo. That's a here. Heat and jilt is how you deal with flows and do you decide to cork a flow or stop tracking a flow or whatever. And then plea is how a vein sends a request to Arvo. So plea and here are kind of our main two that we're going to look at. And then there's some wonderful, so you'll notice that these are like, you can keen or you can yawn. There's all these types that are like, you can hoot to get a, you know, hoot is a request packet payload, or a yowl is a serialized response payload. Like there's all, like everything's noise. This is a loud vein in that sense. But here and plea are kind of our main ones. With gifts, the things that we're getting back, then we are going to be mainly concerned with let's see, what do we, oh, those are the system and lifecycle text. Sorry, I need to be looking at the gifts. The gifts were mainly giving a response with be responding to boons. Boons mean we got something back from it. there's also, you'll notice that plea, what does the definition of plea look like here? Right, every vein can receive a plea note. This is how we're going to redirect from Ames to forward our messages on a peer's vein. So, Gall passes to Ames, passes to Ames, passes to Gall. That's going to go via plea because every vein has the ability to interface with Ames because of this. Like I say, a lot of these are internal. Like you do know what it means to like snub a peer, right? Ames snub, Ames verb. Those are kind of just system operations there. Ames state management. Ames internal state. Let me see if that's in. That must be in Ames.hoon. All right.
I had a quick question, Neil.
Yep.
Sorry.
Go ahead.
Does this mean with the fact that every vein can receive a plea note, is there like a, because it seems to me that Ames must depend on vein because it needs timers to know how frequently to send packets that it's not received acknowledgements for. Do they like depend on one another? Is there just like a cross, or can it not receive? Or is vein one that's excluded from the things that can, the list of veins that can receive pleas?
Let me see if I can find the vein task. No, they all yeah, so these are like every vein has an interface where it knows how to do these things with each other. But these are all in the same top level core. Like this, that's why these are in LOL and not in sys vein Ames. Right? Everything in this core has mutual visibility.
Right. I guess I'm just thinking about this from like a bootstrapping perspective, but I don't think it matters that much because it seems like Ames and vein need one another. Like, well, I don't think that you're often going to be sending Ames packets from vein. Although I don't really know, but that's kind of
because
go ahead.
Right, because Bane would just send a wake
through Ames or just
to Ames. I'm trying to think if there's a let's look at Bane. Let me compare Clay. Yeah, so Bane does not have a plea. Which makes sense because Bane is, you're never going to set a Bane timer on someone else's ship to do a wake up on your ship.
right. So it is, so Bane then is excluded from the list of veins that can send a plea.
Yeah, it looks like so Ames has one, Clay has one. This is air, so it looks like Dill does not, and that makes sense. This must be Gall, of course. Jo looks like Iris does not.
Yeah, and those two do make sense because Dill's like the bootstrapping vein, it like starts all the other veins, so it like would make sense for it to have a dependency in this way.
And then it looks like Con and Lick also do not deal with pleas.
Mm-hmm. Okay,
But I think in all those cases makes sense, right? Like those are not actually veins you want talking.
Yeah, over the network. Yeah, makes sense. Thank you.
Okay, so here's your Ames state, right? So every vein has state that it maintains. Here's your Ames state. So you need to know about peers. Remember ship state we looked at a minute ago, so we could like know like what do we know about a peer? And that the QoS, quality of I don't know, whatever QoS stands for, quality of something. Signal, maybe, I don't know.
Service.
What's that? Service. That makes sense. The Unix duct, which are going to be your moves that are outgoing to Unix. We need to know our life. We need to know our Rift, that stuff. We have an interface to the crypto core stuff, so we can access that. Bug is going to be related to verbosity, so verb would change that. Snub is your whitelist or your blacklist. That's actually interesting, right? We're treating snub as a blacklist, but it looks like you can actually swap it out and treat snub as a whitelist by the form. I'm not sure I've ever seen that done. And then congestion controls, and then
Didn't
Closed
UF do something with sorry, didn't UF do something with like schools that might, I think, used it, that only let them talk to other peers on the network with the whitelist?
was this like an experiment?
I think so. I remember hearing about this, but I could be
Okay.
wrong.
I mean, obviously it's completely straightforward.
Yeah, yeah.
Like there's probably not a hood command to do it, but you could set it,
Yeah.
pass the right card in. Yeah, so anyway, so that gets you peer state. Actually, ship state's an interesting one. That's probably back in LOL. Look what your ship state is. Your alien agenda. Alien agenda means that you're storing, you don't have any PKI data yet, so you're storing queued moves until you learn how to contact the ship. So it's going to store messages, it's going to store packets, it's going to store remote scribes. They're all going to be queued up, and then you can send it. And then known means we do have peer state. Peer state means we have information, right? So this is like where your ossuary is. This is where your key stuff gets stored. I'm guessing we just end up pulling this straight from Azimuth and maintaining our own copy here for efficiency. But, or sorry, straight from jail, but I haven't actually looked yet at the relationship of jail to this part. The cryptography in Ames is like pretty boring. It's just you have an interface and you encrypt things, which makes sense, but there's not a lot else going on. So that's peer state. Okay, Ames has the formal interfaces included more than once. So you remember Arvo? There's like 3 Arvos in Arvo.hoon. Ames has something similar. There's a larval Arvo, there's an external vein interface Arvo, there's an adult, or sorry, there's a larval Ames, there's an external interface Ames, there's an adult Ames that formally pass these things around. So like if I look at Scry's included 3 times, and one of them is just I'm in my larval stage, so skip up to my adult stage if I need to process it. Scry adult core. Well, so here's my actual Scry. There's only one Scry. Everything else is just presenting an interface that gets passed around. So there's all your, there's all your Scries, all the things that you might actually want to pull out here. And then there's a lot of if I look for like mu is my message sender core. So, given a bone and a message pump state, then queue up my messages and then send them to my packet pump to process everything. So there's a lot of these engines that are kind of passing this information around. Then there's also all of the, like I said, the legacy upgrade information. So if you scroll down various places, there's like How do I go from state 4 to 5, from state 5 to 6, state 6 to 7? It's really ugly and messy, and it would be nice if we could figure out a way to actually clean this out, but I don't know if we really can. I don't know, maybe at some point they decide that we don't actually need to care about ships that were booted on a runtime that you'd have to run a host operating system that's 10 years old to even get there. But for right now we have it all in here. So there's all these transition rules between them. Scries are pretty straightforward. Let me see if I have a Zod. Yeah, there's a Zod from earlier today. Right. So if I want to know my peers, then I can ask it for information about, all right, so here's all the peers that my fake ship knows about. If I do an AX scry. So by default, your ship knows about Mr. Distradazad Dazad, Distradazad Dazad, Sawgripe Distradazad Dazad. Apparently I've interacted with Realfet Palsum, and I don't know when, but this was a ship I was testing, so there it is. Interesting that it considers itself to be alien. I don't know if that's standard or not, but it's curious. You can ask about the specifics of, like what is everything your ship knows about someone. This is kind of a neat case there. So Zod is alien, and I have some packets queued up to send to Zod. I am Zod. I don't know why I'm alien, but I have some packets queued to send to Zod as blobs. Let me boot. Let me boot another ship just so I can see. All right, so let's bar high Zod. High Zod successful. Okay, so now if I ask for information about neck, I should get something. Yeah, so now I actually get like much more interesting information, because now I know the key information, the public key. I know the sponsor, I know a route. So this is a direct route, but if it's not a direct route, or sorry, if it's not a galaxy, then I have a lane, and I can see what the IP address is. Right. So I can actually like snoop on information if I know what's going on here. There's not a direct way to, the direct way to get it is to scry into Ames. User space doesn't really have any other tool for it, but you can check these things, and I can see, well, do I have any bones queued up against oh, why are you that to me? I don't know. This is one I tested earlier. Now it's not working for me.
Is it send with an E, or is it SND?
Where's that?
Right there. SND have bones.
No, I think it's SND. Anyway, okay. Well, not doing it now. That's fine. Anyway, the point is, right, there's a lot of Ames information you can actually get information to if you're trying to figure things out. But again, Ames is a thing that you're not going to go delve into like super deeply unless you're actually working on Ames. Ames.c. So, we took a look at this a minute ago. Probably the most interesting things are, so we saw the czar callback. This is our galaxy address resolution, which, we use to actually get our galaxy information. Goes in, it looks up these particular values here. Maybe let's look at send CB. This is our send to callback. Okay. As before, libuv is our loop handler, right? That's our event loop handler that's doing all of our, how do you queue up messages? How do you do everything? So libuv, fortunately, knows how to send UDP packets, among other things. And so when we need to send something, we're going to pass it through the send callback, which means we've gotten some message here. We put it into our event queue in our runtime. Now the Ames send CB gets called, and we actually go ahead and evaluate this. This is the result of we've sent the message, and now the send callback gets called to deal with, did we actually manage to send it? Can we clear up anything, in our queue or whatever to do it here? Does it actually stand for Unicorn Velociraptor? That's amazing.
Isn't it? That's from their GitHub. Isn't that great?
That is great.
Yes.
Mars is built on the backbones of unicorns and velociraptors.
Very much so.
That's
It's so
fantastic.
good. It's so good.
I love it. And then the receive callback is also interesting because this is, where a message has come in. Now we need to process this and inject it back into Arvo. So it can fail in the runtime for some reason. Like you receive a partial message and there's a hang up, or it's messed up or whatever. Otherwise, then we need to go ahead and actually call Ames here, which is going to Ames here. Yeah, this is going to parse our packet and actually inject it into our runtime, wherever it gets injected here. I went taking around for these earlier, but honestly, these files are pretty opaque. I mean, they're not so bad, like once you're in the mindset, of like, I'm in this file and I see what's going on, but a lot of these names are just pretty opaque. I like the, our Hungarian annotations on the end of them. Anyway, so this is what actually processes it, and then it injects it as an Ames here back into Arvo, comes out of this C function here. Yeah. And then we've got a packet, and we're back in Arvo, and we can process it. All right. Now the next thing I want to talk about is FinA and remote scry. So before I pivot to that, do you have other questions about Ames or observations? All right.
Uh,
Go ahead.
I could, I guess. I won't waste everyone's time.
What's the question?
So I have a PR up to basically use the persistent cache to make it so we don't have to sort of manually deduplicate messages that we send out, because we only, I guess, keep something like one copy of each unique message.
Okay.
And so if we send, like if you're a publisher with an app, you don't keep separate copies of that app around for every single subscriber that you have, sort of deal.
Yeah.
But how do I benchmark the difference with and without memoization?
I mean, I guess you'd want to
'Cause
send the same. I mean, I guess it depends on which part you're memoizing, right? Because if the message number is part of it, then that's going to change every time. So you have to make sure you're actually memoizing the blob. Right? Like the thing you want to memorize is the jammed packet content.
The memoization part is, I think, correct.
Okay.
It's basically, I'm just figuring out how to benchmark it.
Yeah. So part of your problem is like there's so much crap happening on a network all the time that it's actually hard to benchmark a network.
Maybe, oh yeah, because
Because anything
I
else that
can't
goes
do
on
fake
your network.
ships.
Yeah, well, and fake ships don't mean anything, right?
So publish a private desk.
Why don't fake ships mean anything in this case?
Well, I
still have
guess
a
they
network
do because
connection.
they are still sending packets.
Yeah.
Okay, so I'll just do it local to,
Yeah, I guess
you know, control that
send
variable.
10,000 copies of the same packet.
Can I publish a private desk with something? Because it can't go over Finet because it doesn't have this problem.
Well, desks go out over Finet, don't they?
Apparently not if it's a private desk.
But how do you expose a private desk to someone else?
Whitelist,
Can you whitelist the desk?
I guess. I just have been given breadcrumbs.
I don't know that I would do it that way. I would send a large noun over the network a bunch of times between two Gall agents.
Okay.
Because then you know you're sending it over Ames.
How do you do that?
Like, how do you send? I mean, it's like you just send the same poke over and over and over again. Right? Build a list of 10,000 cards that's the same poke and poke the other agent 10,000 times and do it with or without
Oh.
Siglas.
Okay.
Or maybe you do
Alright,
them in different events rather than like all in one event. But like that's basically what you're doing.
I may get around to this.
Mhm.
It also will probably be a clear win either way. So it's like, do I spend twice the amount of time with the benchmark, but then it took to do the memoization? Well,
Yes.
I guess so, because we need
Yes.
graphs. We need
Yes.
graphs.
And we need to know what changes you've made.
I think
Like
Puri
how-
was showing off something like this in Lisbon, just like a thread to spam something.
Oh yeah, we were actually doing that. I gotta bother him tomorrow and see if we can finish it. Okay.
It's no bother.
Period.
Okay. Joseph has a question. Did anyone ever pick up the grant to simulate network weather to help with testing something like this? No, I don't think anyone ever did. I'm ambitious to actually come back to this problem after Ares is running. And actually work on like trying to upgrade Urbit as a sort of like a systems engineering test framework, test harness that includes things like that. So I want to revisit that question.
That would be great. That would be like an excellent, I think, a huge win for the ecosystem. Anyway.
Yeah. All right. Any other Ames? If not, then Finet. All right. So scry is a read-only request into your scry namespace. So to scry, you have to bind a value into the scry namespace first. And then, of course, historically, you could only do local scries because scries were synchronous and you did them with .cat. With remote scry, now you can scry over the network, but now it's an asynchronous read, which means you have to send a card and receive a response, receive a gift back. It's a little bit clunkier. But basically, the tasks you have are you can keen or you can yawn or wham. You don't yawn or wham nearly as much as you keen. So you keen to ask to request a value. You can request either a specific case or you can request the latest case, either way. And then it's going to return to you a tune, which is the value you get back, and it has like some hash information and everything with it as well. It's kind of a big data structure. Have any of you worked with remote scries yet?
Not me.
Okay.
I've played with it. I haven't implemented anything.
Let me actually, I'm fresh on this because I just implemented them in Emissary this week. Well, last week. I did it on the plane. I had to debug everything this week. So let me show you what remote scries look like in practice before we talk about how they work.
All black.
Yeah, I know.
Yes,
I'm
for
gonna.
me. Oh,
Oh, did it switch to Emissary?
no, it's just all black.
Okay, that's because I have another screen in front. I'm switching my screen share here. All right, so what's going to happen is when you change the state of something, you're going to pass a card that's a grow card to some path. And then it's automatically going to increment the case. So every time I pass a grow card to fin at outgoing, it's going to bind to emissary faz case faz outgoing. And then it'll return the information that I'm binding here is a cage of, in this case, a set ship. So that's what this line is doing. And then what happens is I will request information with a tune, or sorry, with a keen, looking for a keen. Okay, so now I'm passing a keen to emissary fine, which is the path that I bound above at the time. So it's a keen task to Arvo to that ship, and then I'm asking it for the value at this particular path. And then because I do a double faz here, it gives me the latest value instead of the numeric value that I specify here, which is kind of a weird pattern, but it works. And then what happens is I pass this, so now I'm going to get back a tune, and that tune I have to like variously unpack the data and figure out exactly what's inside of it. So it's a little bit clunky, but that's your basic life cycle is. So like I get an Ames tune back in my on Arvo arm. And then in this case, I'm passing the tail of it because I don't care about the Ames tune at the beginning of it. So I'm passing the tail after that. So like that's your use pattern for what a remote scry looks like. It's not too bad, but you can't use it in line. So now when we come over to LOL, or sorry, to Ames, all of the fin stuff is at the bottom of the file. There's a core that deals with it. But basically there's a keen state. Let me find the original keen state. Oh, that's probably in LOL. Yeah, there's the current keen state. And so this is going to keep track of its own field of request packets that have been sent and unsent, and the number of fragments and the next wake up time to send it along, whatever. So it's really similar, but it doesn't maintain like its own message flows and bones and everything. It's just like, I know how to send information is all it's knowing how to say in this case. So it's actually a little bit simpler mechanically than Ames. But once you've bound it in the run space, it doesn't hit Ames again. or excuse me, doesn't hit Arvo again. So what happens now is when you get a request, it's gonna go to FinA here request. And that request is gonna come in and you're gonna check one of these checks the cache. It might be this. Which one of these checks the path? Somewhere here it checks the cache. Yeah, FinA get cache. So, do I have this value in my scry cache? And then pass this value back out. Otherwise. Yeah, so it gets the path. It does a lot of checks and building the message and everything, and then it actually goes and gets the value in the cache, and then passes this value back out. Right. So the point of remote scry in this case is that your runtime can handle it. It never hits Arvo. It doesn't generate an Arvo event, and we've eliminated not only spurious events that would cause processing, but we've also eliminated another denial of service attack vector by doing this. And so when you register something that goes into FinA put cache here, yeah, and knows to pass those out and everything. So anyway, this is what FinA is doing. It's handling when the event request comes in the runtime, it can handle it all in the runtime and doesn't generate an Arvo event. And then the response goes back as a nicely formed Urbit response tune gift that you can deal with on the other end. I guess it's not actually a gift, it's a note, but and then it's a task, or it's a note, yeah. Yeah, so that's the way that runtime scry dispatch ends up working in practice. There's some other boilerplate around them, like there's a way to tombstone. One of the events that you can pass in is these are all remote scry things. Anyway, somewhere it has a way of tombstoning old paths. And as a practical matter, I'm actually finding that to be a good thing to do. It's not currently built into Emissary, which is what I was looking at a minute ago, but it's good to do because the problem is you bind things into the scry namespace, it's a noun, right? Like a noun is bounded to the scry namespace. And so if you decide to update or change a data type, now you have basically a stale bound scry that will return the wrong data type to you. And this introduces all sorts of interesting errors. In addition, these are kind of hard to test right now because you can't clear them other than tombstoning them. Like once you build a new fake sod, you bind a scry path in that fake sod, it is now part of that fake sod. You can tombstone it, but you can't clear it and go back to 0 on your case. So we'll have to decide what is the right test pattern to make those a little bit easier to work with for people. But yeah, so like I say, FinA is kind of a lot simpler. One of the goals for the next year of kernel development is to unify Ames and FinA back into a single protocol. I guess the difference there would be, if you get a Keen, it would then be a Keen Ames task. It would go into the runtime, and the runtime would catch it there, but it wouldn't be like a sort of a separate protocol channel the way it is right now. Which will be, I think, pretty straightforward. It might also open up the possibility of moving some other parts of Ames into being runtime handled. When you know that the value hasn't changed and it's been cached like Siglas or otherwise, then maybe you can return it as a value without actually having to be concerned about hitting Arvo with it at any given point. Questions about Finay?
I've just got one quick one, which is that you were talking a little bit, Neil, about how with how Finay is implemented, it doesn't actually have to hit the event loop, and so like that has all sorts of benefits. Is that just because of how it was implemented, or is there something specific about like conceptually remote scry that makes that possible, and how it's sort of like enabled with like exposing an endpoint and this sort of thing?
I mean, it was a design. It was a design goal of Finay.
And so is that like something that would be, in unifying the two, is that something that would be like impossible to do with Arvo, or excuse me, with Ames, to keep it?
No, it's not. It's just that Ames isn't designed for that now, and so we have to decide how do we want to expose read-only requests into Ames? Do we want to do some of those in Arvo? Yeah, so Ryan says, noteworthy that large remote scry responses still hammer the receiver's event loop until we shift packet deserialization to the runtime. Yeah, that's true.
But
Yeah,
like,
the fact that it's read makes sense. Yeah. Go
well,
ahead.
yeah, it's because we have like, what is it, referential transparency, that we can do this with reads, so that we don't have to.
You don't have to
like-
note anything. Not like with if we're actually transferring packets, I need to like send you something that you need to record, then that's a different story.
Exactly.
Yeah,
Like once it's bound, it is fixed.
Right.
so how does tombstoning work? Well, tombstoning actually changes the scry handler to say not that we're going to give you no value, but actually that we refuse to serve the request to the path that could have been previously bound. So it's a little bit of a cheat,
I thought we replaced that tombstoning, replaced it with the hash.
I don't know.
Yeah, maybe
Does
you're right. I'm not sure.
tombstoning in Finay work the same way as tombstoning in Clay?
I don't think so.
I don't know.
I don't
So
know.
I don't know. This is something to get
I
into.
think it's probably a
Um,
similar concept with different implementation details, but
Yeah. I mean, well, I alternated it because we're doing Air and Iris next week because those are a little bit lighter weight because they're just HTTP servers, and then we're doing Clay in 2 weeks, which is going to be another big one. Really, the last big one until we get to the Azimuth stuff, though. Gall is actually incredibly straightforward.
Wait, really?
Yeah.
Okay.
I mean, what is Gall? What is Gall? It's a database that knows how to route moves that modify the state of doors.
I guess so.
Like, and actually
Yeah.
the homework, I actually have not decided what would be a good homework for Ames. But the homework for Gall is going to be write a Gall, which is not hard. So